Okay, here's a lesson about geometric sequences. I'm doing it live on YouTube. I don't expect anyone to be watching it actually at 5 o'clock in the morning, but here we go. Okay, so we're familiar with arithmetic sequences, where each term is obtained by adding a fixed value to the previous one. So for example, the sequence 3, 5, 7, 9, 11. Each time you're just going plus 2, plus 2, plus 2, plus 2. So that's known as an arithmetic sequence. You're adding something each time, and then you get the next value. But we're going to talk about geometric sequences. And in a geometric sequence, each term is obtained by multiplying the previous one by a fixed value. Okay, so I suggest you pause the screen here if you're not one of the 2 people remarkably watching it live. So pause the screen on the recording of this that most of my students will be watching, and take a note of that, please. Okay, so I'm assuming you've done that, and I'm going to rub all of this out now. And here is an example of a geometric sequence. So 2, 4, 8, 16. Each time, so it's not going up by a fixed amount, but each time you're multiplying by 2 to get to the next term. So the amount that it's increasing by is in itself increasing, because you're multiplying each term to get the next one. And I've made a table of n and nth term. So when n is 1, we're talking about the first term. So the first term is 2. The second term is 4. The third term is 8. The fourth term is 16, and so on and so on and so on. So we could carry that on. The fifth term, the sixth term, the seventh term, and we can make a prediction by keep on doubling every time. So 16 times 2 is 32. 32 times 2 is 64. 128 for the next one. So it's easy to keep predicting the next term and the next term and the next term. But of course, if you want the 100th term, you don't want to be working out the previous 999 terms. So what we'd like is a rule for the nth term where we just stick the n in and it tells us what the term is. So we're going to look at an approach for doing that. So I'm going to say the first term is just 2. The second term is 2 times 2. And then the next term after that, you're multiplying by another 2 again. So it's 2 times 2 squared. And then the next term is 2 times 2 cubed. Next term is 2 times 2 to the power of 4. So you can just imagine each term as being something that you can write as the first time multiplied by a number of 2's. The next term is 2 times 2 to the 5, and then the 7th term is 2 times 2 to the 6th. Once you've established that pattern, you can start to see the links between the n's, which are the position in the sequence, and the terms themselves written in these particular ways. So for example, the 7th term is 2 times 2 to the power of 6. The third term is 2 times 2 to the power of 2. They're all 2 times 2 to the power of something, and the power number there is always, in this case, 1 less than the position you're on in the sequence. So if I wanted the 100th term, I could very easily predict that that's going to be 2 times 2 to the power of 99, which is a very big number. And in general, the nth term is going to be 2 times 2 to the power of n minus 1. So that gives us a rule where we can work out any term in the sequence, and you don't need to work out all of the previous terms. You just need to know what the position is in the sequence. So for example, if I wanted the 10th term, that would be 2 times 2 to the power of 9. And that's something I could relatively easily work out on my calculator. Easily. I can do that on my fingers actually. 2, 4, 8, 16, 32, 64, 128, 256, 512 for that bit, and then times 2 is 1024. So I didn't have to work out the previous 9 terms to get the 10th term. Okay, oh, lost a viewer on the live stream. There we go. So I'm going to do that again for another sequence. 2, 3, 4.5, 6.75. So again on this one, each term is obtained by multiplying the previous term by something. And if you can't spot what that is, I mean, it's times 1.5 each time to get the next term. And if you can't spot what that is, well, you can just divide any term by the previous one. So 3 divided by 2 is 1.5. 4.5 divided by 3 is 1.5. So you can figure out what you need to multiply each term by to get the next one just by going backwards and dividing it. Okay, so again, I'll make my table. First term is 2, second term is 3, third term is 4.5, fourth term is 6.75. So n is the position of the term in the sequence, and you've got the nth terms. So the fifth one will be 6.75 multiplied by another 1.5, which I can, I've got my hair in the way of the thing again. 6.75 times another 1.5 is, this isn't the world's best calculator, and I'm not in the world's clearest light, but let's see if we can do that. 6.75 times 1.5 equals, you probably can't see that, 10.125. 10.125. Okay, so I can keep on multiplying by 1.5 to get the next term and the next term. And I can think of each of these terms as the first term multiplied by a number of 1.5s. So the first term is 2. The second term is 2 that's been multiplied by 1.5. The third term is 2 that's been multiplied by another 1.5. So 2 times 1.5 squared. The fourth term is 2 times 1.5 to the power of 3. The fifth term is 2 times 1.5 to the power of 4. And you can see that these power numbers are increasing, and they're always one less than where we are in the sequence. So if I wanted the 100th term, let's say, if I wanted the 100th term, I could easily predict that the calculation for that is going to be 2 times 1.5 to the power of 99, which is something I could do on my calculator if I wanted. And if I wanted a general rule for the nth term, that would be 2 times 1.5 to the power of n minus 1, where n is the position we're at in the sequence. Okay, so one last one. This time the terms are 10, 11, 12.1, 13.31. So you can just check by dividing these backwards. 11 divided by 10 is 1.1. 12.1 divided by 11 is 1.1. 13.31 divided by 12.1 is 1.1. Each term is the previous one multiplied by 1.1. So the first term is 10, the second term is 11, the third term is 12.1, the fourth term is 13.31, and so on. And you can think of each of these as being the first term, 10, multiplied by a power of 1.1. So the first term is 10. The second term is 10 times 1.1. The third term, you're multiplying by another 1.1. So that's 10 times 1.1 squared. The next term is 10 times 1.1 cubed. So it's always first term times 1.1 to the power of something. And that something in the power is always one less than the n you're up to in the sequence. So if I wanted, for example, let's say the 1000th term this time, I could easily predict that it's going to be 10 times 1.1 to the power of 999. And I can generalize that to make a rule that in this case, the nth term is 10 times 1.1 to the power of n minus 1. And in fact, if you study this a bit further, you'll see a very general formula that the nth term of a geometric sequence is always AR to the n minus 1, where A is the first term, R is the common ratio between terms, 1.1 in this case, and n minus 1, number of terms minus 1. Okay, but that's just for a little bit later in your mathematical career. That's not the point of this video right now. And in fact, these formulas even hold for the first couple of terms, because if you think of the first term as being the 11, so that's 10 times 1.1, which is the same as 10.1.1 to the power of 1. So 1 is just less than 2. And even the first term, 10, you can think of as 10 times 1.1 to the power of 0, because 1.1 to the power of 0 is just 1, because anything to the power of 0 is 1. So that rule for the nth term is absolutely consistent throughout the whole thing. And here ends the video. Let's just click to end the stream.